Is my screen visible?
Yes, sir.
Yeah, okay. Okay, this is where I stopped, right?
Yes, sir.
Okay. Okay, the major reaction which takes place in phase 1 biotransformations are oxidative reaction, hydrolytic, reductive reaction, oxidation, hydroxylation, reduction reaction. Okay. The key player, right? The main enzyme which is involved in this biotransformation is cytochrome P450. We have different isoforms of cytochrome P450. So almost all the enzymes, they actively participate in the biotransformation of drug molecules. Okay, so few important points related to cytochrome P450, a family of enzyme that catalyzes the biotransformation of drugs, wide range of chemical structure. So we have, as I said, we have different isoforms of P450. So different isoforms can taken the drug molecule as a substrate molecule and they can metabolize the molecule. The major component of cytochrome P450 is like this cytochrome P450 will be having a heme part. Okay, so okay, so let me show the cycle, right? So you can easily understand. So before going for the cycle, these are the various important isoenzymes of P450 protein molecule. So we have CYP1A2, we have CYP2B6, we have CYP2C8, CYP2C19, CYP2C9, CYP2D6, CYP2E1, CYP3A, 3A4, CYP3A5, CYP3A7. So these are the most common, very important isoforms of cytochrome P450. And what are the various drug molecules which are metabolized by CYP1A2, like caffeine, paracetamol, theophylline? So these are the common drug molecules which are mainly metabolized by CYP1A2. So like that, the drug molecules which are mainly metabolized by CYP2B6 or uh, cyclophosphamide, methadone. So these are the common drug molecules which are mainly metabolized by CYP2B6. So the drug molecules like paclitaxel, okay, so it can easily get metabolized by the cytochrome P450 isoform called as CYP2C8. So like that, omeprazole is a drug molecule which is metabolized by CYP2C19. So ibuprofen, warfarin, these are very commonly used drug molecules. So these are the drug molecules which are metabolized by CYP2C9. CYP2C9 is considered as one of the very important isoform of cytochrome P450. So codeine is metoprolol. So these are the drug molecules which are very commonly metabolized by CYP2D6. So alcohol, paracetamol, again, no, very common chemicals which are metabolized by CYP2E1. So indinavir, nifedipine, simvastatin, these are antiviral drug molecules which are mainly metabolized by CYP3A4 or CYP3A5 or CYP3A7, right? So this is very important for if you go for any competitive examination, they may trigger some question related to, so what are the important cytochrome P450 enzyme isoform? And what are the corresponding drug molecules or substrate for that specific isoform of cytochrome P450? So this you have to remember for examination point. Okay, so this cycle is called as a P450 cycle, and so as we said that oxidation, reduction. So this is a common reaction, very simple reaction which converts the lipid soluble molecule into more water soluble molecule in phase 1. biotransformation. So this cycle is called as P450 cycle. So because this entire cyclic reaction takes place with the help of the enzyme cytochrome P450, right? So the cycle starts here. The drug molecules enters into the cycle. So in this cycle, the drug molecule is represented as DH. Okay, drug molecule. So drug molecule which goes and bind to the cytochrome P450, any of the isoform that I have discussed in my previous slide, which goes and binds to the cytochrome P450, right? Each of this blue color and pink color square boxes which represents cytochrome P450, right? Drug molecules, it goes and bind to cytochrome P450. So the architecture of cytochrome P450 is like this P450 will be having heme. So you might already studied about hemoglobin. Okay, so the hemoglobin, it will have a prosthetic group, right? So it will have iron as the metal center. So similar to that, this cytochrome P450 also has the iron metal center. So it goes and bind to the metal atom which is present in the protein molecule. So the metal is in its Fe3 plus state. So once it forms a complex like Fe3 plus DH complex. Okay, so in the next step, what happens is the electron is taken into the cycle. The electron can be taken either from NADPH P450 reductase, or it can taken from cytochrome B5. So any of this can act as a source for the electron. The electron is taken from any of the source, enters into the cycle, and because of the intake of electron, the Fe3 plus is converted into Fe2 plus. So now the system is having Fe2 plus and DH drug complex. So immediately after to that, O2, the oxygen molecule enters into the cycle. So which converts the Fe2 plus DH into Fe2 plus O2 DH complex. Okay, again, a proton and electron, which is the source for this proton and electron in this point is can either taken from NADPH P450 reductase or cytochrome B5. Okay, the proton and electron enters into the system, and because of the entry of this proton and electron, the Fe2 plus O2DH is now converted into Fe2 plus OOHDH complex. So immediately after to this step, there's a release of water molecule from this. So H2O, water molecule is released from this complex Fe2 plus OOHDH, which turned this Fe2 plus OOHDH complex into FeO3 plus DH complex, then which is converted into Fe3 plus DOH, and finally the product is released as drug OH, and the cytochrome is recycled for the next cycle. Okay, so cytochrome here, it is acting as a kind of enzyme which enhances or support this reaction. That's all. So finally we will get the cytochrome P450 for the next cycle. So initial form of the drug molecule is a DH. This is the first step of the cycle. The last step of the cycle is release of DOH. So definitely we can say it's a kind of hydroxylation reaction. The OH group is added to the drug molecule. So the nature of this OH group is it is polar in nature. So initially the drug molecule is considered as more soluble in lipid. Now because of the addition of this OH group, the drug molecule is converted into more polar, or it can easily get soluble in any aqueous solvent. And this cycle is an example for how a non-polar drug molecule is converted into a polar drug molecule which can easily excreted from the system. Is it understandable?
Yes, sir.
Yeah, okay. So this cycle is very important for examination point, called as monooxygenase P450 cycle. Okay, so this is very important for examination point again, because what type of reactions are possible in phase one, and I have given here one example for such a reaction. So the first reaction, very common reaction, is any kind of oxidative reaction that can take place in the phase one biotransformation. So aliphatic hydroxylation is the first reaction, a very common reaction in phase 1 metabolism. So example is this is a original drug molecule having some functional group, okay, to which the OH group is added. Just now I explained in the previous slide, right? So addition of one OH group. So this reaction is an example for aliphatic hydroxylation. So hydroxylation is addition of the OH group. Okay, so why it is called as aliphatic hydroxylation? Because this R group as well as this CH2CH3 group, they are aliphatic, they're not aromatic. So this reaction is an example for aliphatic hydroxylation. So second reaction is the aromatic hydroxylation. So the parent molecule is having aromatic ring system. So this is an aromatic ring system. So how do we say whether it is aromatic or aliphatic? There is a rule called as Huckel rule. 4n plus 2 pi electrons. If any system is having 4n plus 2 pi electron, okay, then we can say that that system is example for an aromatic system. So if you take benzene or any similar organic molecule like this, definitely we can say that it is an example for aromatic system, because this molecule will obey the Huckel's rule. So here some R group is there, right? So after the hydroxylation, what happens? Addition of OH group. So we can say this second reaction is an example for aromatic hydroxylation. And third reaction is N dealkylation. So alkyl is CH3, CH2, CH3. These are example for alkyl groups. Okay, so N dealkylation means the removal of the CH3 group or CH2, CH3, whatever it is, right? So the parent compound is RNHCH3. So after the enzymatic reaction, this parent molecule is converted into RNH2 plus CH2O. So if you look at the product, there is no presence of CH3 group. The CH3 group is completely removed from the parent molecule. And such a reaction is an example for dealkylation, removal of the alkyl group. The fourth common reaction is O dealkylation. Okay, so here you can see the CH3 alkyl group is attached to O. That O is represented here, O dealkylation. Okay, the alkyl group is directly attached to O. So after the reaction, you can see the product is having ROH. There is no more CH3 attached to the parent compound. So again, we are removing the CH3 group, which is attached to the O. That's why it is called as O dealkylation. And the fifth reaction is deamination, very important reaction, considered as one of the very important reaction in phase 1 metabolic conversion. So this group is called as amine here, NH2 group. So the parent molecule is RCH-CH3 NH2 group. Okay, so it's a two-step process. In the first step, some chemical reactions are taking place. We can say alkylation, hydroxylation is taking place. There is no OH group in the parent compound. After the first step, you can see the parent group. Okay, so in the second step, still we have the amino group, but in the second step, what happens? The NH2 group is removed from this molecule. Okay, so we can say that this molecule is now more polar comparing to the parent compound, and the reaction that lead for the conversion of non-polar into polar is the deamination reaction. So the sixth reaction is N-oxidation reaction. So this is the parent drug molecule having the functional group like R1NH2. Okay, so one OH group is added to this, and this is an example for oxidation, because this OH is attached to directly to the NH by removing the H attached to the N. So the seventh reaction is S oxidation. So which means that something related to sulfur. So the parent compound is R1S2. So after the enzymatic reaction, you can see there is a addition of oxygen. So addition of oxygen is an example for oxidation, right? So we can say these are the very common reaction that takes place in phase 1 metabolism. Corresponding drug molecule is given, right? So whatever reaction I have explained is with the help of very simple illustration. So you have to refer some materials for how the ibuprofen is undergoing aliphatic hydroxylation, or how the propranolol is undergoing aromatic hydroxylation, and so on, right? So I give one a small task now. So can you take the structure of ibuprofen now? So what it explain is how the aliphatic hydroxylation is possible for ibuprofen. First question: how the aliphatic hydroxylation is possible for ibuprofen? What is the site of the reaction you had mentioned? And after the aliphatic hydroxylation, what will be the product of the ibuprofen? I'm putting three questions here. Is my question understandable?
Yes, sir.
Again, I repeat the question. First, you have to draw the structure of ibuprofen. Second question is you have to identify what is the site in the ibuprofen for aliphatic hydroxylation. Third question is what will be the product after aliphatic hydroxylation. Okay, so you can try to answer my question, and I can give maximum 5 minutes time for you. End of the 5 minutes, I'll ask someone to share your screen. So what is the structure of ibuprofen? Okay, you can note down this is the structure of ibuprofen. CH3, CH3, CH2, which attached to one of the hydrogen of one of the carbon of the benzene ring C6H5. Then we have CH3 COOH acid group. So what is the site for aliphatic hydroxylation? So here we have the example for aliphatic hydroxylation RCH2CH3, where there is an addition of OH. So if we take ibuprofen as an example, where this reaction will take place, that's a question. So anybody got answer? Harish.
So,
Yeah, where the reaction will take place.
so I'm just looking for it, sir.
Hmm?
I'm just looking for it, sir. Just found some images, but
Okay,
it's
okay,
quite
okay, okay,
unclear.
yeah, okay, okay, okay. Okay, just check it, right? So you may take it as a homework, right? So better you take ibuprofen, and you have to tell that how the aliphatic hydroxylation is possible in ibuprofen, and what will be the resulting metabolite of that reaction. Second, you take propanolol in this second example, and you have to explain with the help of structure of propanolol how the aromatic hydroxylation is possible and what will be the final product. And you take a codeine in the third one, and using the codeine you have to explain that how n dealkylation is possible in codeine, what will be the resulting metabolite. And using the same codeine you had to explain how O dealkylation is possible, what will be the resulting metabolite. And in this you can take a diazepam, very commonly used drug molecule, and you have to explain that how deamination is possible. And using this drug molecule you have to explain that how n oxidation is possible. And using this cimetidine you had explained that how yes oxidation is possible, right? So before coming for the next session, you should have answer for how all these drug molecules are metabolized by aliphatic hydroxylation or aromatic hydroxylation or n dealkylation or o dealkylation or deamination or n oxidation or xs oxidation. Okay, so you can take it as a homework, right? So coming to the this, so far what we have discussed the kind of oxidation reaction, amination, deamination reaction, hydroxylation reaction. But in phase one, the reduction reaction is very rare, or we can say it is very uncommon or less common, right? So we cannot expect many drug molecules to undergo the reduction reaction. So here, this is an example for a reduction reaction, and this is a drug molecule, and these are the metabolites after the reduction reaction. Okay. So what are the common reactions in phase 2 biotransformation? As we discussed earlier that mainly the conjugation reaction will take place in phase 2. The meaning of conjugation is adding two or more components together. So the drug molecule is added with some other endogenous molecules which are present within the body. Okay, this addition reaction is what is called as the conjugation reaction. Okay, so what are the key player for this conjugation reaction? Definitely, this reaction also takes place with the help of enzyme. All the biotransformation reactions within the body cell or enzymatic reaction. Who are the key player? Acetate, it plays important role. Glucuronate, our body is having different types of glucuronate. No, the cells can take use this glucuronate, and it can conjugate acetate, glucuronate, or sulfate or glycine to the drug molecule to make the drug molecule highly polar, which can be easily excreted from the system.
So, can you repeat what you said, sir, about acetate, glucuronate, and all?
Sorry.
Uh, you said something about acetate and glucuronate. So, can you repeat it?
Okay, 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 fine. So so far our knowledge is that if you have a drug molecule, right? So normally the drug molecule will be more lipid soluble than water soluble. If you compare the solubility of the drug molecule to lipid and water, they will be more of lipid soluble than water. First point. The second point is why the metabolism is taking place to convert the lipid soluble molecule into a highly water soluble molecule, so that the body can very easily excrete the molecule through urine or in any other ways, right? So we can classify this biotransformation reaction into two types. One is the phase 1 biotransformation, another one is the phase 2 biotransformation. So the normally the drug molecule will undergo like it goes to the phase 1 reaction. It goes to the phase 1 reaction where it the enzymes prepare the drug molecule for phase 2. So once if the phase 1 reaction is over, that product will be taken for phase 2, and finally the product of phase 2 reaction will be eliminated, excreted through urine, because they will be completely soluble or highly soluble in water. There are certain drug molecules which can directly enter into the phase 2 without going for phase 1 reaction. That is also possible. Okay, there are certain drug molecules which can directly metabolize, which can directly excreted, even without undergoing the metabolism process. All the three scenarios, cases are possible for drug elimination or excretion, right? So coming to phase 1 and phase 2, phase 1 reactions, mainly oxidation reaction, very rarely reduction reaction, hydroxylation reactions possible, deamination reaction is possible. Many reactions are possible in phase 1. Similar to that, phase 2, mainly the conjugation reaction will take place. The meaning of conjugation reaction is the drug molecule will be taken, and the drug molecule will be attached to some other endogenous molecules within the body. So here the meaning of endogenous molecule is, we have different metabolic pathways. So there are, every minute body synthesize different types of molecules present within the body. Maybe some of those molecules may be highly polar in nature. Those molecules can be taken and attached to the original drug molecule to convert the non-polar drug molecule into highly polar drug molecule, right? So what are the endogenous molecules which are very frequently used for this conjugation reaction? The cell uses the acetate molecule, it uses the glucuronate molecule, uses the sulfate molecule, it uses the glycine molecule. If you take acetate, glucuronate, sulfate, these are considered as highly polar in nature. We can say these are polar molecules. So if you attach the acetate group to the drug molecule will become highly polar in nature. Similarly, if you attach glucuronate to the drug molecule, glucuronate is kind of glucose molecule having lot of many number of OH group, so which in turn convert the drug molecule into highly polar. Similarly, if you look at the sulfate is highly polar in nature. If you attach sulfate to any drug molecule, the drug molecule will be converted into highly polar. Is it understandable?
So,
Yeah. So this attachment will not take place on its own. Definitely, even though it is a spontaneous reaction, the attachment of the acetate or glucuronate or sulfate will not take place on its own. All these reactions are possible only with the help of certain enzymes. So we can say that both phase 1 and phase 2 reactions, the key player is the enzyme. Okay, all those are enzymatic reactions. So what are the enzymes which plays important role? If it is a if the conjugation is if the system is going to conjugate glucuronate, and we have an enzyme called as glucuronyl transferase. Okay, so it belongs to transferase family. It's an enzyme. So what it does is it takes the glucuronate molecule. This is an example for glucuronate molecule. You can see it's a 6-membered ring. Like sugar, it is a 6-membered ring having many number of OH group. We can definitely say that this molecule is, could be highly polar in nature because of the presence of many OH group along with 2 oxygen atom. So with the help of this glucuronyl transferase, if you have any drug molecule, okay, the main job of this glucuronyl transferase is it takes this drug molecule, it takes this glucuronate, attach both. Okay, so if I show this image, you can easily understand. This is the same thing what I discussed in my previous lecture. Okay, this is conjugation. Are you able to understand? So aspirin is converted into salicylic acid. We can say this reaction is a hydroxylation reaction, addition of OH group. So from the phase 1, it goes to phase 2 reaction, which is conjugation reaction, in which the system uses some endogenous ligand molecule. Glucuronide here is the endogenous ligand molecule, which has many number of polar functional group that is attached to the original salicylic acid, which converts the entire molecule as a highly polar molecule, which can easily get excreted through urine. because it can easily get soluble in the water. Same thing I am explaining here. Okay, here you should know what is the enzyme which which plays a role. Okay, so for this conjugation of drug molecule to glucuronate, the enzyme that plays an important role is glucuronyl transferase enzyme. Is it understandable?
Yes, sir.
Yes, right. So the next enzyme is N-acetyl transferases. Okay, so what it does is it takes the drug molecule with the help of this N-acetyl transferase enzyme. Okay, this enzyme attaches acetyl CoA enzyme. So again, if you look at the structure of acetyl CoA enzyme, you can see many number of the OH group. So it is highly polar in nature. Okay, so which in turn converts the original highly non-polar drug molecule into a polar drug molecule, right? Second enzyme is N-acetyl transferases. So the body is having a lot of sulfonic acid. Okay, so what it does is, we have enzyme called as sulfotransferases, which mainly participate in the conjugation reaction in phase 2. So it takes up the drug molecule with the help of this sulfonyl transferase. This enzyme attaches the sulfonic acid. Again, if you look at the structure of sulfonic acid, we have many number of polar functional group. Attachment of this sulfonic acid, this is called a sulfation, literally, right? So this sulfation reaction lead for or converting the highly non-polar drug molecule into a highly polar drug molecule. Is it understandable?
Yes, sir.
Yes, right. So now, if we summarize whatever we have studied, we can classify the biotransformation into two types: phase one biotransformation and phase two biotransformation. So, set of chemical reactions which are we studied. What are the chemical reactions which are feasible in phase one metabolism? Also, we discussed about what are the chemical reactions which are possible in phase two metabolism. So phase two is mainly conjugation. Phase one is oxidation, reduction, alkylation, amination, whatever reaction right. So almost every reaction is possible in phase one. So both phase one and phase two reactions are taking place to convert the less water soluble drug molecule into more water soluble drug molecule, so that they can easily get out of the body, excreted through urine. There are certain drug molecules which may not undergo either phase 1 or phase 2 metabolism, because already they may be highly polar, they can easily excreted through urine. There are certain drug molecules which may undergo first the phase 1 reaction, then after the first metabolic conversion, the product of the the product of the phase 1 reaction may enter into the phase 2 reaction, and finally the product of the phase 2 reaction can easily get dissolved in water and eliminated from the body. There are some drug molecules, certain drug molecules, which can bypass the phase 1 reaction, directly enter into phase 2 reaction, where the conversion will lead for increase in the water solubility. Drug molecule can easily eliminate it. And one more point is the cycle of the P450 enzyme. So how this oxidation, reduction, alkylation, deamination reactions are taking place with the help of P450 cycle. That's very important for metabolism. So any question up to this? Any questions?
No.
Somebody is speaking but not audible. You can also type in the chat box. If you have any question, you can put it in chat box. Any questions? Okay, so then, okay, the next topic is stereo selectivity of the drug molecule for cytochrome P450. Um, the metabolism, depending upon the structure of the molecule, the, the metabolism route may get differ. Okay.
அதனால இவங்க வந்து எடுக்கிறதுக்கு வந்திருக்காங்க. அவங்க சொல்றாங்க நீங்க கிளாஸ் பக்கத்துல வைக்காதீங்க உங்களோட ஆட்டோகிளேவ் அப்படின்னு. நம்ம முன்னாடி இடத்துல வச்சிருக்காங்க. அது வந்து யூபிஎஸ்ல இருக்கும்.
So if we will take this warfarin as an example, because it's a standard example used for explaining the stereo selectivity of the drug molecule for metabolism. So this is the structure of warfarin. Obviously you have to remember the structure of warfarin. This is the structure of warfarin. Can you make a guess whether this molecule is highly polar or non-polar? Am I audible?
Yes,
Yes.
Yeah, my question is whether this molecule will get soluble in water or not, or whether it will get soluble in lipids. Is my question understandable?
yes, sir.
Somebody can try to answer. I am showing some structure. We discussed so many, we made so many discussions related to the water solubility and lipid solubility.
Non-polar, sir. Non-polar, sir.
Non-polar, right? So we can expect this molecule to be more soluble in lipids, right?
Yes, sir.
Yes, right. Okay. Warfarin, I'm not going detail, right? So it is having a chiral center, and this point, what I'm labeling here, the dot is the chiral carbon. Okay, because of the presence of the chiral carbon, this molecule can exist in uh, different structural form. That is what we call it as a stereoisomer. Okay, so because of the presence of this chiral carbon, it can exist as stereoisomer. Okay, so if you look at this structure, say this is image one, and this is structure one, and this is structure two. Okay, so can you tell what difference do you find between structure one and structure two? Let me erase this for clarity. Yeah, what is the structural difference between the molecule one and two? Do you find any structural difference?
Hydrogen position, sir.
So can we say the position of these two functional groups are changed? Am I right?
Yes, sir.
So can we say molecule 1 and molecule 2, they are stereoisomer?
Yes.
Yes, right. So they are stereoisomer. Okay, let me write here. They are called as stereoisomer. 1 and 2, they are stereoisomer. If any molecule exists in stereoisomeric form, then it is not necessary that they have to follow the same path for the metabolism. The metabolic path may get differ, right? That's a topic, right? So stereo selectivity. So stereo selectivity arises if any drug molecule has a chiral center or stereo chiral carbon, right? So in this example, this carbon is the chiral carbon. So with respect to this carbon, four different groups are attached: R1, R2, R3, and R4. So this is R1, this is R2, this is R3. Whatever is present in this region is R4 group. So four different groups which are attached to the central chiral carbon. Then there is possibility for enantiomer, stereoisomer. So in that aspect, we can say molecule 1 and molecule 2 are stereoisomer. They are non-superimposable mirror image. If any drug molecule has chiral carbon. If any molecule has stereoisomer, if any drug molecule exhibit stereoisomerism, then it is not necessary that all the isomer will follow the same metabolic path. The metabolic conversion path will get differ. Say for example, this is an example for S warfarin and this is R warfarin. As we said, S and R, the relationship is they are non-superimposable mirror image. So S warfarin undergoes metabolism and converted into 5,6 hydroxy warfarin. On the other hand, the R warfarin, they can metabolized using two different pathways. One is called as the major route, another one is called as the minor route. If R warfarin is metabolized through major route, then the final product metabolite is RS alcohol derivative. If it uses the minor route, then the final product will be RR alcohol derivative. Okay, the point is that it is not necessary that both the enantiomer should follow or end up with the same metabolite. The metabolic path may differ if they are enantiomer, if they are stereoisomer. So since the path varies, definitely the final metabolite will also get vary. Is it understandable?
Yes,
Yes,
sir.
sir.
Yeah. Okay. Okay. I think that's all for this session. Any question I can answer. Otherwise, we will continue in the next class. This topic is over. So I need to talk about the excretion process. What are the various factors which affects the excretion in the next lecture? If you have any question, I can answer. Otherwise, we'll wind up the session. I gave some homework. No, you can do the homework. You have any questions?
No, sir.
Okay, then we will do one thing. We wind up the session. So I gave 5 drug molecules. You have to draw the structure. And while coming for the next class, I need the answer for all the drug molecules. Okay. Is it fine?
Yes, sir.
Yeah. Okay. Okay. Thank you.